Hi there guys, well welcome back. We're about to do 4E and 4E is pretty exciting. We're going to do differentiation from first principles. So we're now about to hit into the start of differentiation in our book. Okay, well some of you might know already a little bit about differentiation. Some of you might know the rule for differentiation, or some of you might know what the meaning of it is. So first of all, let's just talk about the meaning. What we're looking for and what we're interested in is how to work out the gradient on curves. So we're interested in finding the gradient at any particular point on a curve, and that's going to depend on x. So what we want is a gradient function. And the gradient function we call the derivative. So, for example, we can see, we have a look at the black line, which I've just put on Desmos. If I take this point further round, this is a tangent to a line. In fact, this turns out to be y equals x squared. And if I move my point where the tangent touches the curve around, then what I'm looking for is the gradient of that straight line, or the gradient of the tangent at any particular point. You see at the bottom, at 0, it's 0. And you can see, here we go, at 1, it's got a particular slope. And it's getting steeper and steeper as we go up this way. Okay, so we want a function for that, and that's what the derivative is about. It's a gradient function. Now, for those of you who know the rule for this for polynomials, so where you've got certain amounts of x to the power of n, and so for people who know that rule, we're not looking at the rule just yet. We're looking at kind of more fundamentally here, how do we develop the rule, or how do we take a function, so let's take any function, maybe a polynomial, and apply a technique of differentiation by first principles to get down to that gradient function. So whereas some people might have seen a rule from before, that perhaps was never proved. Now what we're talking about now is proving it in particular cases and giving you the means to prove that for particular cases as well. And from that, you can develop on the rule. Okay, so I've just set up here on Desmos. You can see y equals x squared, or f of x. I think I called it at the top. There we go, f of x is equal to x squared. That's my red graph. And you can see I've just talked about the tangent line, which is created there, which is me just moving around this blue point here, and that's giving me this tangent line. And I can zoom out if I want to. I can zoom in, but I don't particularly want to. There you go, there it is. I'm just going to pull that over to the side for a moment, though, just to take that out of the way. And I'm just going to get rid of that. Now, you might actually be interested in the functions which I've created here, which is not really what I mostly want to talk about today. But here's my functions I've created for h of x, that black line, this function here, which actually includes derivatives. So I'm using derivatives within this program. That's where you see f dash of x. I'm using derivatives to make these functions, okay? But all I'm doing at the moment is showing you what a tangent line is. Now, you might be interested in that. You might be interested in trying to make that yourself in a bit as well. So I'm just going to get rid of that line. Okay, so now that line has disappeared. And now what I'm going to show you is this line here. So what we looked at with that black line was a tangent to our original function. And now what we've got is a secant. Okay, so a secant is a line which crosses our f of x. And in this case, it crosses it twice, but I haven't actually drawn it beyond those 2 points. Now, I put in a massive function for this one. And I could have sped it up if I'd used derivatives as well, but I didn't. I actually, I was just sort of working that one out. But either way, that's not what you need to worry about at the moment. That g of x, that massive function there, which I've created, don't worry about that. Worry about what it's doing. Okay, because what I'm going to show you is that here's my 2 points here, and I'm going to bring them sort of closer together. And I could take it to the other side, but there we go. I'm going to keep it on this side here. Now, this is what's going to lead to differentiation from first principles. Now, I also made a table in Desmos as well, and that's really easy to do just by typing table. And I think I changed y1 to f in brackets of x1 because I'd set up not y is equal to something, I set up f of x is equal to something. So, okay, so that was pretty easy to do. But that's just plotting my point there. I'm plotting my point 1, 1. and I'm plotting my point A and 7.84. Look, I can plot other points here, and I can plot 2, and I can plot 3, and I'm just plotting those points, but I don't want those points. I want this point A. Now, the A point is a generic kind of point, which I can just pull up and down, and I've been able to do that by creating this equation underneath and this slider here. So here we go. I can create that slider. It's just sort of coming backwards and forwards. But again, I'm not interested in it being over there. I'm interested in it being in somewhere in this range here. Likewise, I can press play on that B slider, get that tangent moving as well. Desmos is really nice for this kind of thing. Okay, so there we go. I've got 2 points there. Now, the theory behind differentiation by first principles is essentially to say, well, we can't work out the gradient at a particular point because gradient is change in y divided by change in x. And so at a particular point, we have no change in x if we use the same point twice. In other words, x1 take away x2 on the bottom is going to give you a 0. You can't divide by 0. That's undefined. We have this real problem here of thinking, well, which 2 points do we take? Now, it's possible you could take a point which is before my example point here, which is 1, 1, 1. You could take a point before and then a point after and then kind of average it out. But that's not really great. And what we're going to do is actually take a point which is beyond our original point here. So our original point being 1, 1. And we're going to take that point which is beyond, and we're going to say, well, the gradient of this line here is very close to the gradient of the tangent. And as we bring that point even closer in, we're getting extremely close to the gradient of the tangent. So what we're going to do is bring 2 points really, really close together, and we're going to take the limit of the difference between those. So the increase in x value, we're going to take the limit of that increase in the x value to 0. So we're going to bring those 2 points together, if you like. But of course, we can't actually divide by 0 in a gradient function. Now, I'll explain that a bit more algebraically in a moment as well. Just to put that tangent function back again. So here's the tangent function. Let's just bring b up to 1. Okay, so there we go. B is equal to 1 now. So that's our tangent. And let me just change in here for g of x. Let me just change this to, so my limits for the domain for this function, I'll put in a 0.5 and a plus 0.5 here. So let's go a little bit beyond. Let's take that secant a little bit further beyond. So now when I take a further up again, so there we go, we've got, those are our 2 points which we're trying to bring together. And as we bring this point A closer and closer together to the original point, which I'm taking as 1, 1 here, although it can be any point. But as I bring those 2 points closer together, you can see that I'm getting closer and closer to the gradient of the tangent line, which is the black line there. Okay, so that's what I'm aiming to do. And you can see when I'm really, really close here, when I'm really, really close, the tangent is almost the same, but still not quite. Okay, well, that's the theory. And let's actually look at the algebraic practice here. So we've got, this is kind of a general version. So I just took off my axis points here, and I'm just going to call this instead, well, I could call it x, and in some books you see that called as x. And in fact, in our book, they call that a. And I'm just going to call this our function for x here. And so the coordinate point that you're getting out here, when you put in a, is going to be f of a. So you put in a, you're going to get out f of a. Now at this point over here, I'm going to call this point, so just taking it further up, I'm going to call this point a plus. Now this is, I don't know whether I should be consistent with the book. The book says a plus h. Well, I feel like I'm doing you an injustice there to not call it a small amount more of x. Okay, so that's what I'm going to call it. Remember, delta, capital delta means change in or at least often it means changing in our in mathematics, in our formulas. And so if we use capital delta, we'd say, for example, change in y divided by change in x is equal to your gradient. We know that between any 2 points, we do a change in height divided by change in distance across gives us our gradient. Okay, but if you use the lowercase delta, that's seen to be a small change in. Okay, and so that's what we're interested in here. We're interested in a small change. So that's what we're going to use here, small change in x. Now, in the book, they're using plus h, and we're going to just show that's exactly the same as well. But the reason why I'm using delta x is because you might be aware of dy dx. So we're going to end up with this when we do something with this in a bit. Okay, so we're going to end up with that notation. Now, dy dx, just to jump the gun a little bit here, dy dx is our derivative function. That's our gradient function. That's m, which is dependent on x. Okay, our gradient at any point, like, or what some people will call in functions notation f dash of x. So this is going to be our gradient function. That's the reveal for later on, which I've kind of spoiled now. Okay, so when we put in this function, this value for x into this function, we're now getting out a height of a plus delta x. Now we've chosen a instead of x because a is a particular point for x here. We could have chosen x as a kind of generic point, but then it gets confused with the sort of f of x up here as well. And you can see that, in fact, it's the right thing to do that. Like in my formulas, which I've got here, I've put in a, I've put in b for particular points rather than our general variable, which we're substituting in there. Okay, so we're kind of ready and set up now to do our to find our formula here. So our formula in this case, or in all cases, in fact, for that we would use, which we would start with for differentiation from first principles, is your change in y. Okay, so your change in y, which normally we're going to write like that if we're talking about average change, but here we're talking about a small change. Okay, so we're going to do a small change in y divided by a small change in x, and this is giving us our change in y there is going to be f of a plus delta x, take away f of a, so that's just the change in height, divided by, and we're getting here the small change in x is going to be actually just delta x. Now, if you want, you can type this in as, write this in as a plus delta x take away a. So it's the distance here. Okay, so what we're trying to do is divide, we're making this triangle, we're trying to divide this delta x here, sorry, delta y here, by the delta x. Now, delta y is the change in height between this and this. And delta x, well, is just delta x. It's the change here and here. If I take that back a little bit, I'm actually just going to write that as delta x as well. There's no need to overcomplicate that one. Now, as we bring these points closer together, so in other words, as this tends to 0, we end up getting our gradient formula, which is going to give us our derivative. So what we're going to do is say we're going to take the limit of delta x, that says lim, delta x tending to 0 of this delta y of a delta x. And when we take that, that's the same as saying taking the limit or as delta x tends to 0 of this thing here. Sorry, I can't fit that one in there. Okay, so that's going to give us our gradient at our particular point when we bring this point infinitely close to a. So we're tending towards 0 there. And we bring these 2 points infinitely close together. Now, this thing here is in fact called dy dx. That's the same thing. That's your derivative. Now, when we apply our properties of limits to whatever function we end up getting in here, when we choose a particular function, we should be able to apply those properties of limits or algebra of limits and actually work out this function here, which will give us this function in terms of x, which we're also calling f dash of x. So, okay, that's all quite theoretical here, but you can see why delta y over delta x becomes dy dx, and that's the definition for this thing here. So when I write dy dx, I don't mean something divided by something. I actually mean this as a definition for something. This is, if you like, m, but m is dependent on x, or at least it should be in terms of this function if all your function in terms of x here as well. Okay, so let's just have a look at what the book is doing as well. The book does this through a little investigation, of course, and then it talks about the average rate of change here being delta y over delta x is equal to, you know, the change in height between your 2 points divided by the change in distance across between your 2 points. Now, it defines secant and tangent. There you go. And there's a little investigation there as well. So I've kind of done that stuff for you a little bit. But you can have a look at that investigation as well. But so then it's saying that, sure, we've got this average rate of change, but there's a bit here which it says as h approaches to 0, sort of in the center of the page there, is the gradient of the tangent at A, this point coordinate A that they're talking about, where they're now using x rather than lowercase a, frustratingly, is the limiting value as h approaches to 0. Now, when they say h, they mean delta x. Okay, h is that little extra bit on x, which you can see in their little diagram over to the right-hand side. Okay, so now they flick back the x and f of x in this in their little red box here, and they've changed the x f of x to a f of a. So they're talking at this point a f of a, then our gradient of the curve at this point, at this particular point, is the limit of h tending to 0 of a f of a minus h minus f of a divided by h. Okay, that's the same as what I've got. Okay, right. So maybe I misspoke a little bit earlier as well, because I'm just thinking that when we put in a, they're quite right to say, let's just look at that again. They're saying that this is the gradient at any point. So a comma f of a. And I was saying, well, this is going to give us a function of x. Well, in fact, actually, it will give us a function of a, the point that you're putting in. But if we change this a to our x, then we're going to get a function in terms of x. Okay, so we're going to go from we're going to move from this particular point to just saying, well, we've got any point here. And so if we want to substitute in not just a, but x, seeing as this is going to work for any point, then that's going to turn into a function of a. That's going to give us this dy dx. Okay, so let's just take some of this back for a moment. And I'll tell you what, I'm now going to go with their version here. So this f of a plus h minus f of a, this thing here. In fact, okay, well, I want this thing up still. But what I'm going to do is I'm going to prove that the derivative of f dash of x is equal to 2x. We've got the original function f of x is equal to x squared. Okay, and we'll talk about the meaning of that at the end of this too. Now, I'm just going to change the a in this to x. Okay, so we've got our limit as h tends to 0. I'm going to go with the h. I'm going to say f, in this case, I'm going to say f of x plus h. And then I'm going to do minus f x, and then I'm going to do divided by h. So this is going to give us our derivative. So this is going to give us y dx. So our derivative in this case. Now I'm not going to do it at a particular point. I'm going to do it for a general point. Now, again, you could put in a, and then you could say, well, this is working for all values of a, so now I'll change my a to x, but I'm just going to do it straight away with x. Okay, so this coordinate point here is going to be x comma x squared, and this coordinate point here is going to be our small amount more of x. Okay, so x plus that small amount more. And then we've got x plus h substituted into the function, because the function that we're considering here is f of x is equal to x squared. Now, we might have to do this for x cubed, we might have to do this for 1 over x, but we're doing it in this case for x squared. Okay, so now when we substitute in f of x plus h, that's giving us this thing here. So again, we've got the limit, can't lose that, as h tends to 0 of x plus h all squared, and then take away x squared because that's f of x. Now, when we divide these two here, that's still the change in distance across of h between those 2 points. Okay, now we can multiply this out, so we've still got the limit, we still need to keep that in, okay, and we now need to multiply this out, so we're getting x squared plus 2hx plus h squared minus x squared, and then divide by h. So the x squared and the x squared is going to cancel that. Now, next line is still, we've got the limit as h tends to 0, because again, we can't divide by 0. That's our issue. Now you can see that you can factorize on the top line, so you're getting 2x plus h, and then we've got the h on the bottom, so the h and the h can cancel. Now we've got the limit as h tends to 0 of this function 2x plus h. Now, as h tends to 0, that's going to disappear, and since 2x is not dependent on h, we can say that this is equal to 2x, and now that is done. We have proved that the derivative, or the gradient function, for y equals x squared, let's just call that y as well because I've used y there. So we've proved that the gradient function for y is equal to x squared is 2x. Now, what does that tell us? That tells us then that when we have the coordinate point 1, 1, we have a gradient of 2, plus 2 times 1. When we have the coordinate point 2, 4, you know at that particular point, the gradient is 4. Not because of this, but because of this. We need to double the x value. The coordinate point 3, 9, we know that we have a gradient of 6 because of this, 2 times x. The gradient function is dependent on x here. Okay, now there are cases where gradient functions can be dependent on x and y, but currently we're not dealing with those ones. Okay, so that's pretty nice. If you've never seen that before, that's going to take a little bit of going through, and you might need to repeat this video or try and figure it out from the book as well. But yeah, that's gradient from the gradient, finding the gradient function or finding derivatives from first principles. Okay, just to talk about the formula though, some people might know that if you take x to the n, that takes you to n lots of x to the n minus 1. Some people might know that you can times by your power and then reduce your power by 1 for every polynomial, or every power of x rather, within your polynomial. So if I had a k there as well, I could just put a k in front here as well. Okay, now that's the rule for taking the derivative of any power of x. Now, some people will already know that. Sorry if I've spoiled it for other people. Okay, so let's look at the book, and yeah, let's see what they've done there. So they've actually said, look, let's find the gradient at the point -2, 4 in the book here. Okay, and you can see that they've done that using the particular point A. Well, obviously that's done with the particular point A there, but I did it with the general point x, x squared. So you can obviously do this for particular points as well, but I'm not going to do it for this particular point. But you can do it for the particular point. Okay, now for the second one, find the points of on the graph of y equals 1 over x where the gradient is -1/4. Now they're taking any point here and they're working with any point, and they're working with that any point as a. Now again, you can work with that with x like I did before there as well if you prefer to. This time around I'll do it being consistent with the book, and So let's do this one then. Okay, so example 12 says find the points on the graph where the gradient is equal to this. So essentially we need some sort of gradient function which is now dependent on a, and we're going to need to set that to minus a quarter to give us out particular values of a, which is the same, frankly, as getting out particular points of x. Doesn't really matter. Okay, so let's do this one then. So the gradient function, of course, is our dy dx. Now here I would write dy dx rather than f dash of x, because it's stating y rather than f of x. So dy dx is asking us to do the limit as, and we'll go with the h as the book does, the limit as h tends to 0 of our function f of a plus h minus f of a, and then divide by the small change in x on the bottom there as well. Now let's take that a little further. So we can see we get still the limit as h tends to 0 of a plus x, sorry, a plus h inside this function here. So we're getting 1 over a plus h, and I know we're using a combination of function notation and this y. It's okay, but function notation is really quite good when we're substituting things in. Anyway, so we've got minus 1 over a here and then divided by h. Well, now it just requires us to do some algebraic working out to bring these two things together. So if you want to maybe do that aside, you could say I'm doing this aside to the examiner. Okay, and we can see that we're getting times the top and bottom of that fraction by a, and then times the top and bottom of the second fraction by a plus h, and we're getting a plus h in there. And then when we do our subtraction, we'll have a, take away a, and then we'll get minus h at the top there. Okay, so there we go. I mean, you can always do a little working out aside, just make it really clear that you're doing that. So we're getting minus h over a, and then a plus h there, and then that's divided by h as well. Okay, now when you divide fraction by another fraction, you could write that as well if you want to, as instead of this thing on the bottom, you could say divide by h over 1, which is the same as, of course, timesing by 1 over h. And then that's going to that h is going to cancel with this one here. But I think a lot of people can see straight away that, you know, say for example, if you divide 2/3 by 2, that you can cancel the 2 out and you'll end up with 1/3. Okay, so the h and the h is going to cancel there. Okay, so now we've got, and let's take this minus out the front. Okay, because we can do that. That's allowed in our algebra of laws of algebra with limits. And then we're left with inside 1 and a. I'm going to multiply that thing out at the bottom. We've got x squared, a squared plus a h there. Okay, well now it's really easy to see that as h tends to 0, this term is going to disappear. And this is just some constant according to the limit. So that's not dependent on h. So we can now do the limit here. So we can now get rid of this thing here by then saying we're going to end up with 1 over a squared with a minus on the front. Now, if you're interested in doing this via the other method, well, just via the rule, we can see that we've actually got y is equal to x to the minus 1. If you times by your power, so dy dx, our gradient function, is the same as timesing by our power, so we get minus, and reducing our power by 1. Now you can see that's essentially the same thing as this, although we're saying here for a particular point, and this is just saying for a general point. Okay, so the rule of timesing by the power and reducing the power by 1, we've just verified also works here as well. Okay, well, we haven't finished the question because it says find the points on the graph where the gradient is equal to this. If you know, if by the way you get this question in an exam, you're not going to do all of this. because the question doesn't say do this by first principles, but at the moment it assumes that we don't know the other method of using the rule. So, of course, now to solve that equation, we're going to need to set this up as equals to minus a quarter. And so therefore, a squared is equal to 4, and a is equal to plus minus 2. So 2 values. Oh, and it says work out the points. So more than that, we actually need to substitute those points in as well. So when x is equal to minus 2, y is equal to minus a half, and when x is equal to 2, we're getting out y is equal to plus a half. And you can put those, of course, in coordinate points as well. When it says points, I would actually then go ahead and put those into coordinate points there too. Okay, well, let's see what they do. Let's see what they've done here. Yeah, they've put them in coordinate points as well. Right, well, we've got there. We're up to exercise 4E, and you've learned, hopefully, the basis of this idea of differentiation, and you've learned how to do differentiation by first principles. Now, just a note on this exercise, what I did with f of x equals to x squared, you're now going to have to do with f of x equals to x cubed and so on. I can see x cubed turning up at part E there, but they're saying as well at a particular value of x. And so, in fact, you can actually put in that particular value and work with that. Now, here we go. This is me getting a little confused here, I suppose, because now it's saying that the gradient function is actually not just for a particular point, it works for all points if we just change that a to x. So I've kind of done a mixture of both formulas there. You can see that the questions are talking about at particular points, which is what exam questions can ask as well. But like the technique which we did for that last question, all in terms of a, to get out your function, and the function was minus 1 over a squared, you can do all of that with x in just the same process, and then we have essentially found our derivatives from first principles as well. So obviously, the next exercise is going to go through examples like that. Okay, right, I'll stop there, and thanks for listening in, and hope to see you back for the next one.